Okay, so our first presentation today is from Jonathan Crabbé. Jonathan is a PhD student who joined our lab last year, and it's on machine learning interpretability. Jonathan, if you wouldn't mind sharing your screen over mine.
Of course.
Thank you.
So hello, everybody. My name is Jonathan Crabbé. I'm a second-year PhD student at the Schaar lab, and today I'm very happy to share my research with you. So as you can see in the title, I'm going to talk about time series models and how to explain their predictions. Before talking about this precise subject, I'd like to mention that I'm only going to cover the tip of the iceberg today. So obviously, we have done much work on interpretability. And if you want to know more about what we have done, please check this website here. And this will give you a lot of details on our work on feature selection and symbolic metamodeling, which of course I'm not going to cover because of time. So everybody uses the word explainable AI, and this is somewhat a vague term. I'd like to spend some time now to define more clearly what I mean by that, to ensure that we are on the same page. Modern machine learning models are typically black boxes that eat inputs and spit out predictions. The purpose of explainable AI is to understand what happens in this black box. How is the input X transformed into a prediction Y? This is definitely not a trivial question because modern machine learning models typically involve millions of operations to turn their input into a prediction. So there are multiple ways of answering this question. So today I'd like to focus on one, which we call post hoc explainability. The idea of post hoc explainability is that you add a module on top of the black box. This module is aware of the black box as well as the input. And in this way, for each prediction made by the black box, it outputs an explanation. So you might wonder what these explanations look like. Well, to give an illustration, it is useful to take an image classifier. How can we explain that this black box here recognizes a dog on this picture? Well, a first example of explanation is through feature importance. The idea here is to highlight the part of the input that are important for the black box to make the prediction. For instance, the model might pay attention to certain part of the image to identify a dog. A second approach is given by example-based explanations. These explanations will typically contextualize the prediction by presenting similar examples from the training set. The third example is given by rule-based explanations. These methods present a reasoning that might involve some abstract concepts, and by following the reasoning, you arrive at the model's prediction. Of course, those are just examples, and there are other types of explanations which I'm not covering here. But in the following, I'd like to bring your attention on the first one on this list, feature importance methods. More precisely, I'd like to bring your attention to feature importance particularized to the time series setting. However, before going there, I'd like to quickly give some motivation for paying attention to this very restricted setting. A first motivation for focusing on explaining time series model is that time series amount for a big fraction of the available medical data. Whether you talk about electronic health records, survival analysis, or even disease progression modeling, the dynamic nature of the data matters in the medical context. Maybe one reason for this is that time series allow to model an evolution, and in this way, they are more detailed and they give a more detailed story than plain tabular data. Finally, those of you who have worked with time series know that it's often very messy, whether it's a variable length of the time sequence or missing data at some time steps. There are a lot of difficulties that occur in this setting. The very fact that we have these difficulties should hint us to be even more careful with the resulting models, and hence try to better understand what has been learned. So now let us make our setting a bit more precise. We start with our input time series, which represent the variation of some features over time. We feed this time series to a black box and get a prediction that we'd like to understand. In this case, we will explain the prediction by highlighting the part of the time series that are important for the black box. We represent this by a mask that we can superpose on top of the time series to highlight the important parts. So this seems like a simple problem. However, we'll now see that existing methods are not suitable for this setup. So let us first try existing methods on top of a problem where we actually know the solution. Suppose that I start with a time series and a model for which I know where the important part is. This is represented by this true mask that you can see over here. What I can do is use popular feature importance methods like Schaar or Lime on top of this model and see if they recover the truly important part of the time series. So if you do that, you'll notice that those methods identify too many features as salient. On top of that, they produce masks that are not very legible, even though the time series is quite low dimensional, as you can see here. So you might wonder, why is it so difficult? Well, one possible answer is that nothing encourages this method to be parsimonious and highlight no more feature than necessary. If you look closely at the image, you'll notice that true, sometimes important features are identified, but there are also a lot of features that are not important and they are given a big importance score. So this is particularly problematic in the time series setting, where you typically have hundreds or thousands of features with a number of time steps. Another possible answer to this question is that these methods miss an important part of the story. Time induces a context, and the variation of features over time has a particular order. These methods that I have presented here don't take this order into account. This is probably the reason why they don't do very well in the time series setting. Now, actually, I briefly mention what we propose to fix this problem. We introduce a method called Dynamask that is specialized to the problem of feature importance in the time series setting. Let me explain the basic ideas behind Dynamasks. So Dynamask is a perturbation-based method. What does it mean in practice is that important features are detected by studying the effect of their perturbations on the model prediction. To illustrate, I consider a very simple example of a recommender system that recommends me to sell or buy a security by studying its price over time. As you can see, at the last time step, the model wants me to sell. I'm wondering if the previous time step is important for the model to arrive at this conclusion. So what I'm going to do is perturb this previous time step and observe that the prediction changes. So it must be important, right? Now, let me remind you that time induces a context. Ignoring this context led other features importance methods to perform poorly. To address this, we introduced the notion of dynamic perturbations. These perturbation operators use points that are close in time to build perturbations. On this graph, this means that I perturb a point by using points that are close in time, so points that are around it on the graph. Of course, this is only the basic idea, but if you want more detail, I invite you to read the paper. All of this is interesting, but we are still missing the most important part. How do we compute the mask itself? Well, at this stage, it's not difficult. We just have to assemble the pieces of the puzzle. We start with the... As before, the mask represents the part of the input time series that are important. We would like to learn this mask. To do that, we use the mask to build the perturbation of the input. We feed this perturbed input to the black box to get a perturbed output. As I said previously, the mask should ideally conserve the relevant part of the time series and perturb the rest. We can perfectly obtain this kind of behavior by making the perturbed and the unperturbed output resemble each other. We do this by backpropagating the error between these two outputs to correct the mask. This is the blueprint of Dynamask. Now, let me explain some subtleties that might not be obvious from this blueprint. When fitting the mask, you have to pay attention to several things. The first one, as I have said, is that we have to make sure that the mask selects relevant information by making the perturbed and the unperturbed output resemble each other. Then we have to make sure that the mask actually selects some features. Indeed, a mask that tells you that all the features are important is not very helpful. We do that by adding a term to the objective that encourages sparsity in the mask coefficients. Finally, the user might have some prior knowledge or desiderata about the mask. For instance, we might want to avoid too many quick jumps of the importance over time. If this is the case, this can also be encoded in the objective. Of course, now that you have a method, you can compare it to the state of the art. In doing this, we notice three things. 1, Dynamask offers a better detection of important features. 2 and 3, the masks are more parsimonious and more legible than for other methods. If you want more details, I encourage you to read the paper. So I'd like to end this talk with a look on the future. I think that there are many things that could be improved in the approach that I have described here. Firstly, we know that characterizing the prediction of a model just on the basis of the output is a bit reductive. Modern machine learning models typically involve latent representation that allow to transform the input into a prediction. It would be nice to look at these representations to better understand these models. Next, feature importance is nice, but it only tells a part of the story. We know what features are important, but we don't really know why. Contextualizing the important features with relevant examples would be a way to tell a more insightful story. Finally, it would be interesting to provide explanations that clearly indicate when the model can be trusted or not. If you are interested in any of these points, I'm going to present you a new work at NeurIPS 2021 that you might want to check. It is called Explaining Latent Representations with a Corpus of Examples. I really hope you enjoyed the talk. If you want to learn more about the subject, please check my GitHub or my paper. I thank you for your attention.